Section 4.5, example number 3. We need to solve the initial value problem given by the differential equation and the conditions. So, to find the solution of the initial value problem, we need to find first the general solution, which is composed by the sum of the solution coming from the auxiliary equation and the particular solution. Now, the expression for YC, complementary solution. Complementary solution is the solution that comes from the homogeneous equation. And then once we write the homogeneous equation, we need to write the auxiliary equation. And then solve for R. So we solve for R. R is going to be positive and negative 1. So the complementary solution from section 4.2, I'm sorry, 4.3 is going to have the shape, since we have two real different solutions, is going to be C1 e2 dx plus C2 e2 negative x. That's going to be the solution for the complementary part. Now, the particular solution, YP. YP is coming from f of x. But notice that f of x, which is the right, is the linear combination of, remember, linear combination is sums and additions. Sums or additions. So we have the linear combination of different functions. So we have, if you notice, we have three different functions on the right. So we have an exponential, we have a polynomial, and then we have a trigonometric. So we are going to have, for the particular solution, we're going to have three components. The first one is coming from e to the x. E to the x is generating the first component. So e to the x is going to be, in this particular case, x e2 dx. But the reason, what is the reason for which we have this x? Well, we have this x because, remember, the exponent of the exponential is 1x, right? 1x. Here we have an invisible 1x, but this invisible 1x that I'm going to remark with a different color, this invisible 1x, I'm going to do it in red, this 1x is the same as this 1x in the complementary. So that is why we have this term x. This term x that I'm underlining now is because the exponential, or the coefficient in front of x in the exponential, is the same as the one of the roots of the auxiliary equation. So remember, we have the solution of the auxiliary equation. We have 1 and negative 1. So this 1 okay, is the same as the 1 in the exponential. That's why we have an x. The next contribution is going to be from x to the second. X to the second is a polynomial. X to the second is a polynomial. So by itself, x to the second is not multiplying anything. So x to the second, the contribution of x to the second is going to be a polynomial of degree 2, because that is the degree of the polynomial. bx to the second, b1, or b2. You can say b2 b2 plus b1x plus b0. And finally, the trigonometric cosine of x. Let's use different colors to differentiate the exponential in blue, the quadratic or polynomial in green, and the trigonometric in yellow. Okay, so what is going to be the contribution? How is going to be the general form of that is going to contribute the trigonometric? It's going to be C1 cosine of x plus C2 sine of x. Okay, so the general solution, the general form is going to have, or is going to be yp equals to, there is an a here missing, ax e to the x plus b2x to the second plus b1x plus b0 plus c1 cosine of x plus c2 sine of x. And now, remember, when you need to find the general solution, you have to find the value of a, b2, b1, b0, c1, c2. So let's not confuse. Let's change these c's so that there's no confusion with the c's from the auxiliary equation. Let's call them d1, d2. Okay, d1, d2. Okay, so we have to find what is the value of a, b2, b1, b0, d1, d2. So for this reason, we have to find two derivatives and plug them in the given differential equation. So we have first derivative of yp. We need to apply the product rule since we have x multiplying an exponential. So we have a to the x, or derivative of x is 1, so it's simply a times e to the x plus derivative of the second function, which is e to the x times the first, so it's exactly the same thing. Plus, and now we're going to find the derivative of each of the other elements. Derivative of b2x to the second is going to be, I'm going to keep them in parentheses. We don't need it, but I'm going to keep both of them. b2 x plus derivative of b1 is b1. Derivative of b0 is 0 because b0 is a number, remember. Now, derivative of cosine of x is going to be negative, so we have negative d1 sine of x plus d2 cosine of x, because the derivative of sine of x is cosine of x. So we have to find now the second derivative. Then we have to find the derivative of each of the terms from the first derivative. We have derivative of a to the x is a to the x itself. Derivative of ax e to the x, we have to apply the product rule, same as in the previous first term. We apply to find the first derivative. It's going to be a e to the x plus ax e to the x plus the derivative of 2b2x, that is simply 2b2, minus plus the derivative of b1. b1 is a number, so it would be 0, minus the derivative of d1 sine of x, and that is going to be minus d1 cosine of x minus d2 sine of x, because the derivative of cosine of x is negative sine of x. So our equation, the given equation in the problem is y double prime minus y prime equals to 2 e to the x plus x to the second minus 3 cosine of x. That is the given derivative, given differential equation. So it's y double prime minus y equals to 2e to the x plus x to the second minus 3 cosine of x. So y to the second, well, y to the second is this expression, and shaded in this color, that is green, light green, we can say, right? And then we don't have y prime in the given differential equation. We're going to use a different color. A color is this, so we have to use, or we have to replace the expression in light green and in violet. Okay, so we have, here we go, we have what? We have 2a e to the x. Why 2a? Because these two combined elements is going to produce 2, right? 2 plus a e to the x. Well, okay, there's an x missing here. A to the x plus 2b2 minus d1 cosine of x minus d2 sine of x, right? So this expression is the one in, let's say, light green, right? This is y double prime minus y, the expression in pink, I mean in violet, sorry. So we're going to put a minus in front of the expression for yp. So we have what? Negative ax e to the x minus b2 x to the second minus b1 x minus b0 minus d1 cosine of x minus d2 sine of x, and that is equal to the right, which is 2e to the x plus x to the second minus 3 cosine of x. So this I'm going to show you now is yp. And then when the right is the same as, as the expression we have been carrying previously. So these ax e to the x cancel this ax e to the x. So let's now form systems of linear equations to compute the value of each of the coefficients a, b1, b2, b0, D1 and D2. So look at compare the right and the left. Well, we have that 2a must be equal to 2 because exponentials should be equal to exponentials, right? So from here, we conclude that a is 1, right? Now, we are going to put together all the coefficients by uh, itself. I mean, coefficients uh, that are in front of the same letters. So we have, what do we have? We have that 2b2 minus b0, 2b2 minus b0. Okay, let's say um, this coefficient I'm circling and this one is equal to 0 because we don't have any number by itself on the right. Okay, now we also can see that let's see, what do we have? We have that d1, we have two d1s, right? We have this d1 cosine of x negative and this d1 cosine of x. They are the same and we can combine them. And how many d1s we're going to have? We're going to have negative 2d1, negative 2d1. And then negative 2d1 is going to be equal to whatever number in front of cosine we have on the right. So that is going to be negative 3. So from here we conclude that d1 is 3/2 positive, by the way. Now let's combine the d2s. We have negative d2 sine of x and negative d2 sine of x. And then we have negative 2d2. Do we have any sine of x on the right? No. So negative 2d2 equals 0. Therefore, d2 is simply 0. It's 0 divided by negative 2, which is 0. Now, we have that this b1 I'm circling now. This b1, negative b1, negative b1. Do we have any x to the 1 on the right? So, no. So from here, we conclude that b1 is equal to 0. Okay. Now, we have this negative b2 I'm circling now, negative b2. Do we have any x to the second on the right? Yes, we have. What is that number? Well, what is the number in front of x to the second on the right? Is simply 1. So from here, we conclude that b2 is negative 1. Okay, negative 1. b2 is negative 1. Now, we have b2, we have b1, we have d1, we have d2. What is missing? b0. b0 is missing. Well, from this equation that we established previously, we may say that b0 is equivalent to 2b2. Therefore, b0 is equal to 2 times negative 1, which is negative 2. Okay, so we are in conditions to write the particular solution. Okay, we're in conditions to write the particular solution. So the particular solution, remember, the particular solution, yp, is equal to, let me copy and paste if I can. I'm gonna try. Okay, it's gonna be, no, so doesn't matter. I'm gonna write it again. Yp is, or the particular solution is, trying to minimize this so that everything is in the screen. It is what? A to the x, ax, ax, a to the x, plus b2 x to the second, plus b1x, plus b0, x d1 cosine of x, plus d2 sine of x. And now we're going to, put what we found in yp. So what is yp? In this particular case, once we have found the values of these coefficients. So it's going to be, a is 1, so it's going to be 1x e to the x, plus, what is going to be the value of b2? b2 is negative 1, right? b2 is negative 1, so it's going to be negative x to the second, negative x to the second. We don't have any b1. b1 is 0, right? b1 is 0. Then we have also b0 is negative 2. Negative 2 as the polynomial, plus d1 cosine of x. What is the value of d1? d1 we found to be 3/2 cosine of x. d2 is 0, so we don't have sine component. We don't have sine component. So this is the particular solution that you can rewrite it like this. Let me fix this too. Plus 3/2 cosine of x. So it's the same thing, yp. Does this concludes the problem? Not really. Now we have to find the value of C1 and C2, which is the solution of the complementary portion of the equation, of the solution. So we now have to find or use the conditions. We have to use the conditions now. And then we have that. The conditions are, given in the problem, the conditions are y at 0 is negative 1, y at 0 is 3. Y at 0 is negative 1, right? And then y prime at 0 is negative 3. It's positive 3, So remember, this is going to be used to find the values of C1 and C2. C1 and C2 are the numbers that the coefficients of the complementary equation, complementary part of the solution. And the complementary solution is C1 e to dx plus C2 e to negative x, right? We found that before, the complementary. Okay, so we find uh, that y at 0 is equal to -1, then this is equal to C1 e to 0 plus C2 e to the 0. Okay, e to the 0. So we have one system of linear equations, which is equivalent to -1 equals to C1 plus C2. Because remember, e to the 0 is 1. Okay. Now, for this reason, we have to find also the derivative of the complementary. The derivative of the complementary is going to be C1 e to the x minus C2 e to negative x. And we know that the derivative of the complementary is 3, and that is equal to C1 e to the 0 minus C2 e to the 0, which is equivalent to another system, which is 3 equals to C1 minus C2. So from here, we can combine these two equations by addition, right? So we have what? 2 equals to 2C1. 2 equals to 2C1. Then C1 takes the value of 1. Then C1 is 1. Then we can replace this C1 equals to 1 either in the first equation of our system or in the second equation. So we can replace it in the first one, let's say. So we have -1 equals to 1 plus C2, then C2 is equal to -2. Okay, so now we're in conditions to write the general solution. Remember, the general solution is composed by the sum of the complementary and the particular. So it's going to be the complementary. Complementary is going to be 1, which is C1, e to the x, plus 2, plus C2. And C2 happens to be -2, e to negative x, plus the particular. And the particular, we found it before, which is this expression, which is x e to the x, right? Let's wait until it keeps minus x to the second minus 2, minus x to the second minus 2, plus 3/2 cosine of x. And then this is, in fact, the solution of the initial value problem. Okay? And this solve the, this is the end.